In this episode, we will talk about voice-language foundation models for real-time autonomous interaction.
Right. We're going to be exploring something pretty exciting today, actually, looking at the real cutting edge of AI, and specifically how we're shifting away from these voice assistants that just react.
The ones we have now, yeah.
Exactly, towards AI agents that can actually be autonomous, ones that can, proactively jump into a conversation, respond instantly, and even convey real emotion. Think maybe of the AI in the movie Her, that kind of nuanced interaction.
That's a really compelling picture. And it highlights something fundamental about us, about humans, how important voice is.
Mm.
So much communication isn't just the words, right? It's the tone, the rhythm, the pauses, all those subtle cues.
Absolutely. Text is great for some things, but voice, it's just richer. Think about all the things we do with our voices, grabbing attention, interrupting those little sounds that show we're listening.
Back channeling, yeah.
Right. These are crucial for how we talk naturally, and they've mostly been missing from AI interactions until perhaps now.
Okay, so let's dive into that because this leads us straight to Voila. It sounds like a big step towards this more, well, human kind of interaction. What's the main goal behind Voila?
Well, Voila is essentially a new family of large voice language foundation models, and they're specifically built to enable these more natural, autonomous voice interactions. The big difference is moving away from those traditional pipeline systems.
You mean like Siri or Alexa work now?
Exactly. Those systems usually have a whole chain of separate steps: detect the wake word, then automatic speech recognition ASR to get the text.
Then natural language understanding NLU to figure out what it means.
Right, then natural language generation NLG to create a text reply, and finally text-to-speech TTS to say it out loud. Voila uses what's called an end-to-end architecture instead.
End-to-end, so a more unified approach, less like an assembly line.
Precisely. Instead of all those separate stages, Voila aims for something more integrated. This lets it handle full duplex conversations, meaning it can listen and speak at the same time.
Oh, wow. Okay.
With really low latency. And it keeps those vocal nuances, the tone and emotion we were talking about. And the latency numbers are quite something. Voila's response latency is just 195 milliseconds.
195 milliseconds.
Yeah.
That's faster than typical human conversational reaction time, isn't it?
Yeah.
Usually cited around 200, maybe 300 milliseconds.
It is. That speed could really change how natural AI feels. It's not just a bit faster, it's getting close to how quickly we respond in a conversation. That's huge for making it feel fluid.
So how do they achieve that speed?
It comes down to the design. A hierarchical, multiscale transformer architecture. Think of it like a very layered, organized neural network. It cleverly combines the reasoning power of large language models, LLMs, the tech behind things like ChatGPT with advanced acoustic modeling.
Right.
This combination allows it to generate natural-sounding voice that can even be shaped by text instructions to have a specific persona. You could literally describe the kind of voice you want, the tone, the personality.
So we're not stuck with one generic robot voice. You can actually craft the AI's vocal identity. That sounds incredibly useful for making AI feel more believable, more engaging.
And the customization goes further. Voila supports over 1 million pre-built voices. But what's really impressive is how quickly it can learn a new voice. Give it just 10 seconds of audio.
10 seconds.
Just 10 seconds. And it can capture the unique quality, the timbre, the sonic fingerprint of that voice and replicate it.
That's amazing. So I could theoretically give it a snippet of my voice, and it could respond sounding like me.
That's the idea. And on top of that, Voila is designed as a unified model. So the same core system handles not just the conversation part, but also automatic speech recognition, turning speech into text, and text-to-speech, turning text into speech.
All in one package.
Right. And it can be extended with some fine-tuning to do other things like multilingual speech translation. It's about the efficiency of having one integrated model doing all these related jobs.
A truly unified system. And, importantly, the researchers have made Voila fully open source. That's a big deal for pushing the field forward, letting everyone build on it.
It really is. It's like giving the research community a powerful new set of tools to accelerate progress in how humans and machines interact.
Okay, so we have this exciting vision, autonomous, real-time, expressive voice AI. And Voila looks like a serious contender. But to really appreciate what it does differently, maybe we should quickly recap the problems with the older systems. What were their main weaknesses?
Good point. Historically, you had those traditional pipeline systems, Siri, Alexa, Google Assistant back in the 2010s. As we said, a complex sequence of modules: wake word detection, ASR, NLU, NLG, TTS.
Sounds like a lot of handoffs. Prone to delays, I'd imagine.
Exactly. Each module often needed lots of hand engineering, specific data, making the whole thing complex and often limited to pretty narrow types of questions. Then, more recently, with powerful LLMs, we saw slightly simpler pipelines emerge.
Right, where the LLM does the main thinking.
Pretty much. The LLM handles the understanding and response generation based on text, with ASR getting the voice input into text and TTS getting the text response out as voice. ASR and TTS act like bridges.
So leveraging the text smart to the LLM.
Correct. It uses the LLM's knowledge and reasoning, but both the old pipelines and these newer LLM-based ones have some key limitations that stop them from feeling truly natural or autonomous.
Okay, let's break those down. What are the big ones?
First, latency. High latency. Every step in that pipeline adds a bit of delay. Even small delays add up, often leading to response times of several seconds. That just feels unnatural compared to human chat.
Makes sense. The flow's broken.
Second, information loss. When the ASR converts audio to text, you lose all that richness we talked about, tone, emotion, accent, even background sounds that might give context.
Like your example. Oh, really?
Exactly. That phrase means totally different things depending on how you say it: surprise, doubt, sarcasm. Text alone loses all of that crucial intent. The AI is working with incomplete information.
Right, it's missing a huge part of the message.
Precisely. And third, these systems mostly force turn-based interactions, like texting. You talk, you stop, then the AI talks. But real conversation is messy. We use bat channeling, I see, to show we're listening.
We interrupt, too.
We interrupt, we overlap, we speak at the same time sometimes. These pipeline systems just don't handle that dynamic well. It makes the interaction feel, well, robotic, mechanical.
So even if developers bolt on some rules to detect interruptions or trigger proactive comments, it's still kind of superficial. It doesn't understand the flow.
Exactly. Those are often rule-based patches. They don't have the deep context or real-time processing needed for true conversational fluidity. Now, to be fair, there have been end-to-end audio models developed before Voila. Models that process audio directly and generate audio back, skipping the text step.
Oh, okay. So that would address the latency and maybe keep more of the acoustic detail.
Generally, yes. End-to-end models tend to be faster, no text conversion delays. And they can preserve and generate more nuanced audio. But the Voila research suggests that even these models largely stick to that reactive, turn-based interaction style. Better speed, better sound, but still not quite a natural conversational dynamic.
Okay, understood. So pipeline systems have latency and lose nuance. Even earlier end-to-end models are often still turn-based. How does Voila specifically tackle all of this? What's the core idea?
Voila's main aim is to break through those barriers. They've developed two main model types. There's Voila E2, an end-to-end model focused on natural, low-latency conversation with rich voice detail and good instruction following.
Right.
And then there's Voila Autonomous. This one goes further, aiming for truly autonomous interaction, continuous listening, real-time thinking, and full duplex responses, speaking and listening simultaneously. That's the key difference, moving towards an agent that manages its own conversational turns.
Full duplex. That simultaneous listening and speaking really mimics how we talk, doesn't it? With overlaps and interjections being normal.
Exactly. And the foundation for both model types is this innovative hierarchical transformer architecture. It uses streaming audio encoding and tokenization processing audio continuously in real time, and it has multiscale transformers.
Okay, break that down a bit. Multiscale transformers.
Yeah, think of it as having different parts specialized for different jobs. There's a large language model backbone, the part that handles the meaning, the reasoning, and then there's a hierarchical audio generator that creates the voice output. Importantly, the whole thing is trained end-to-end on huge amounts of matched audio and text data.
End-to-end training again, meaning the system learns the whole process, from audio input to audio or text output, directly without needing separate predefined stages.
Correct. The integrated training is key. The researchers highlight a few major advancements from this. First is the really effective integration of voice and language. They've figured out how to blend the LLM's existing text smarts with new abilities to understand and generate voice.
So it's not just translating between speech and text and back again. It's like the LLM itself learns to think in both audio and text more directly.
That's a good way to put it. And a core piece of this is that multiscale transformer architecture we mentioned. It predicts semantic tokens representing meaning and acoustic tokens representing sound characteristics separately at different levels.
Ah, okay. So it separates the what's from the how.
Kind of, yeah. And it lets the main LLM backbone focus on the meaning, which is what it was trained for, while other parts handle the acoustic details, the voice's timbre, tone, rhythm, and so on.
Interesting. Semantic tokens and acoustic tokens. How does Voila actually get these different token types out of the raw audio?
That's where the Voila tokenizer comes in. It's a neural audio codec, basically, a smart way to compress and represent audio designed specifically for this. It extracts both semantic and acoustic tokens from the raw sound waves. These audio tokens are then added right into the LLM's vocabulary alongside its text tokens. It's a clever way to enable cross-modal training, letting the model share knowledge between text and audio. Then, when generating a response, Voila interleaves these audio and text tokens.
Interleave, like weaving them together.
Sort of. It allows the LLM's strength in generating coherent text to guide the generation of equally coherent and appropriate voice. The first level of tokens from the Voila tokenizer captures the semantics, the meaning. The next three levels capture the acoustics, the sound details, speaker identity, vocal nuances. And this tokenizer was trained on a massive 100,000 hours of audio data.
100,000 hours. That's huge. It must have a really deep understanding of speech sounds then. This separation of meaning and acoustics seems vital.
It really does.
Mm.
Now, another big advancement is how Voila handles voices having millions pre-built and creating new ones efficiently. This isn't just a few preset voice options.
Right, you mentioned the 10-second cloning. How does that work technically? And the million voices.
So Voila lets you easily customize and add new voices. You give it an audio clip, could be 10 seconds, could be longer, and it learns a unique voice embedding.
And embedding, like a digital fingerprint for the voice.
Exactly. A compact numerical code that captures the voice's unique timbre, tone, accent, everything. Once it has that embedding, Voila can synthesize speech in that specific voice. And if you combine that embedding with text instructions defining a persona, say, make it sound like an older, cheerful professor, you can create entirely new AI characters with distinct personalities and voices.
That opens up so many possibilities. Gaming characters, personalized assistants, accessibility tools.
Absolutely. And because learning a new voice is so efficient, needing just that short sample, they were able to pre-build that library of over 1 million diverse voices. And finally, there's the unified model aspect.
Unified in what way, specifically?
It means the same core model naturally handles ASR and TTS without needing separate specialized networks for each. Plus, they've shown it can be easily adapted for other tasks, like speech translation between languages, just by fine-tuning it. It already supports 6 languages: English, Chinese, French, German, Japanese, and Korean.
So one powerful base model for many audio language tasks. That sounds much more efficient than building separate models for everything.
Precisely. It really shows the flexibility of their end-to-end unified design.
Okay, let's dig into some more of the technical nuts and bolts. You mentioned the voice tokenizer using RVQ. Can you explain that a bit more?
Right, the Voila tokenizer. It builds on techniques using residual vector quantization, or RVQ. The basic idea of RDQ is turning the continuous audio wave into discrete digital tokens. Voila's version is special because it distills the semantic information, the meaning, into the first level of RVQ tokens.
Oh, yeah.
So level 1 is mostly about what's being said. The next 3 levels capture how the acoustic details, the speaker's voice characteristics, the nuances. Think of it like layers of detail.
Residual vector quantization. Like creating layers of digital representations, starting with meaning and adding sound details.
That's a good way to think about it, yeah. Progressively refining the digital picture of the audio. Now, how does Voila actually align the text and audio information inside the model? They use a couple of key training strategies for that.
Okay, what are those strategies?
The first is called multitask alignment. During training, the model learns several tasks at once: ASR, TTS, and different kinds of instruction following. And all these tasks are framed in a consistent chat format, like human input, Voila output. The model's goal is always just predicting the next token in the sequence.
So for ASR, the input is audio tokens, and it learns to predict the corresponding text tokens as the output.
Exactly. The input might look like human audio tokens, Voila, and the model predicts text tokens, EOs. For TTS, it's human text tokens, Voila, predicting audio tokens, EOs. They also use formats like text-to-text, text-to-audio, TIAO, audio-to-text, AITO, and audio-to-audio, AIAO.
TIO, AITO, AIAO.
And crucially, when calculating the training error, the loss, it only looks at the response part, the tokens after Voila. This forces the model to focus on generating the correct response, not just copying the input format.
Makes sense. Focus on the actual task.
Right. Now, when the task involves generating audio, like in TIAO or AIAO, they use a second strategy. Text-audio interleaved alignment. This aims for really fine-grained synchronization between the text and the sound.
Interleaved alignment. What does that look like practically?
So for the phrase, hello, I am voila, the input sequence might be encoded like this. Hello, audio I, audio am, audio voila, audio. See how each word, each semantic unit is paired directly with its corresponding audio tokens.
Ah, okay, so it's a very tight pairing, word by word almost.
Much tighter than previous interleaved methods like Spirit LM or USDM. Those often alternated longer sequences of text and audio without this strict one-to-one link at the word level. This more direct pairing in Voila likely helps it learn the timing and expressiveness better.
It forces a more precise mapping between the meaning and how it sounds at each moment.
Precisely. Now, thinking about the overall flow, the audio tokens come from that 4-layer RVQ tokenizer. The text tokens are repeated 4 times to match dimensions. This interleaved sequence gets turned into embeddings numerical vectors. These are averaged and fed into the main LLM backbone.
Got it.
Then, the audio transformer part takes the LLM's output and predicts the sequence of audio tokens for the final sound wave.
So the LLM processes this mixed representation, integrating meaning and sound info to generate an output that's right both semantically and acoustically.
That's the idea. Now, for Voila Autonomous, the full duplex one, it needs to handle the user's audio and its own audio simultaneously.
Right. How does it manage listening and talking at once?
It processes both streams in parallel. The user's audio gets tokenized and embedded. Voila's own recent output also gets tokenized and embedded. Then, these 2 sets of embeddings are simply averaged together.
Average. Okay.
This fused embedding goes into the LLM. The LLM then considers both what it's hearing and what it just said to generate the next part of its response. The audio transformer then creates the speech.
So the LLM gets a combined picture of the ongoing conversation from both sides, allowing for that more continuous, less turn-bound flow.
That's the goal, yes. A more fluid exchange. Lastly, the voice customization. How does it learn those speaker characteristics so well? You mentioned special tokens.
Yes. How do those work?
Right. They use these learnable special tokens. Think of them as placeholders in the input that get filled with the voice embedding information. They use a separate tool called WestSpeaker to extract these voice embeddings from audio clips.
What speaker? Okay.
During training for audio generation tasks, they add special tokens like TTS ref start, TTS ref, TTS refend to the input prompt. The actual voice embedding from WestSpeaker gets associated with that middle TTS ref token. This tells the model which voice profile to use. They use different sets of tokens for pure TTS versus conversational chat to avoid confusion.
And at inference time, when you want to use a new voice,
You provide a short clip, WestSpeaker extracts the embedding on the fly, and that embedding gets plugged into the prompt using those special tokens. Voila then generates speech in that voice. Combine this with text instructions for persona, and you get really rich AI characters.
that granular control over voice identity seems absolutely key for making AI interactions feel more personal and, well, human.
It really is. It lets us move past generic voices towards AI that can communicate with much more nuance and personality.
Okay, so to test all this, the researchers created their own benchmark, the Voila benchmark. What's involved in that?
Yeah, they needed a way to evaluate these models on a broad range of tasks and knowledge areas, going beyond just basic speech recognition or synthesis. So they built the Voila benchmark by taking questions and answers from 5 well-known LLM evaluation datasets.
Which ones?
MMLU, that's Massive Multitask Language Understanding, covering lots of academic subjects. Math for math problems. OpenAI Human Evil for coding ability. NQ Open for open-ended questions, and GSM-8K for tricky grade school math word problems.
So taking established, tough text benchmarks and adapting them for voice AI.
Exactly. They took samples from all these, covering 66 different subjects, nearly 1,600 samples in total, all from the official test sets, so the models hadn't seen them before.
But how do you test a voice model on text questions? You need audio input, right, Jen?
Good point. Some samples, especially math formulas or code, don't work well with standard text-to-speech. So they used GPT-4o, a powerful multimodal model, to rewrite those tricky bits into a more TTS-friendly format, keeping the meaning the same. Then they used Google Cloud TPS to turn all the questions into speech audio.
Okay, that's a careful process to create a challenging voice-based benchmark. How did Voila actually do on it?
The evaluation was interesting. They took the audio output from the model being tested, transcribed it back to text using Whisper ASR,
Whisper it.
and then used GPT-4o again, this time as a judge. GPT-4o compared the transcribed answer to the original correct answer from the dataset and gave it a score from 0 to 100 based on correctness and relevance. It's an indirect way to measure if the voice model understood and reasoned correctly.
Right, using a powerful language model to judge the semantic accuracy of the transcribed audio output. Makes sense. So the results.
They compared Voila to two other open-source audio language models, Speech GPT and Moshi. Voila did significantly better. Across the whole benchmark, Voila scored an average accuracy of 30.56%.
And the others.
Speech GPT got 13.29%, and Moshi got 11.45%. So a pretty substantial lead for Voila.
That's quite a gap. Did Voila excel in particular areas?
Yes, it showed notably big gains in the math and coding domains. This suggests that Voila's way of aligning text and audio really helps it tap into the LLM's reasoning power, even when dealing with complex, structured information like math or code presented via audio. The paper has detailed results for all 66 subjects, showing Voila performing well across the board.
Impressive. What about performance on standard speech tasks, like just pure ASR or TTS?
They tested that too. For ASR, they used the standard LibreSpeech test clean dataset, measuring word error rate or lower is better. They tested Voila trained without seeing LibreSpeech data and with it.
And the results?
Without LibreSpeech data, Voila got a 4.8% EAR-ER. That's competitive with top models like Whisper and better than Moshi in that setup. When trained with LibreSpeech data, Voila's WER dropped to 2.7%. That matches the best reported result from another state-of-the-art model called VoxLM. So top-tier ASR performance.
Okay, so it nails the traditional stuff too. What about text-to-speech?
For TTS, they used the evaluation method from Valami, another well-known PTS model. Basically, you generate speech from text, then transcribe it back using a strong ASR, they used BERT large, and measure the WER against the original text.
Right, and Voila's score.
Without LibreSpeech training data, it got 3.2% ER on the transcribed audio. With the data, it improved to 2.8%. In both cases, it significantly beat Moshi, which scored 4.7% on this TTS task.
So it seems strong everywhere. On their complex new benchmark, on standard ASR, and on standard TTS, often state-of-the-art.
Exactly. The evaluations really paint a picture of Voila being a significant step forward for these kinds of voice language models.
Okay, so let's try and wrap this up.
Yeah.
Summarizing our deep dive into Voila, what are the absolute key takeaways here? The main innovations?
I'd say there are several big ones. First, that end-to-end architecture. It delivers the low latency and preserves vocal nuance, getting past the old pipeline problems. Second, the effective integration of voice and language. Using that hierarchical transformer and the clever tokenization and alignment, it lets the LLM's reasoning shine through in voice.
Right.
Third, the efficient voice customization, millions of voices available, plus quick cloning from short samples. That's huge for personalization. Fourth, the unified model design handling multiple tasks like ASR and TTS efficiently. And finally, the strong performance across the board. The new Voila benchmark, standard ASR, standard TTS, proves it's not just theory. It delivers state-of-the-art results.
It really does sound like Voila could be more than just a tool we command. Maybe closer to that proactive, even empathetic partner we imagined at the start, something more naturally integrated into our lives.
That's definitely the vision, the long-term goal. And by open sourcing the models and code, the researchers are really inviting the whole community to build on this, to push towards that next generation of human-machine interaction even faster.
It really makes you think, doesn't it?
Yeah.
About the bigger picture. If we have AI that can understand and talk back, not just accurately, but with human-like speed, natural voice, real emotion, and can even engage proactively, maybe anticipate what we need, how does that change our relationship with technology? Does it even change how we relate to each other? That's definitely something to ponder.